Hi, in this video we'll continue talking about properties of estimators, including sufficient statistics. So a statistic is any function that takes in the data samples x1 through xn and outputs a real number. For example, you could output the sum of the samples, the average of the samples, the max of the samples, or just the first sample, or even a constant. Okay, so let's say that you have ID samples x1 through xn from a known distribution with unknown parameter theta, and you have two people. Statistician A knows the entire sample and sees all n data points, x1 through xn. And statistician B, on the other hand, only knows t, which is a single number, which is a function that is calculated from the samples. For example, the sum or the maximum of the samples. So heuristically, t is a sufficient statistic if statistician B can do just as good of a job as statistician A, given less information. For example, if the samples are from a Bernoulli distribution, then knowing the number of heads is just as good as knowing all the individual outcomes, because we don't actually care about the order of the outcomes, we only need to know how many heads occurred. Okay, so a statistic t is a sufficient statistic if the conditional distribution of the data samples x1 through xn given t and theta does not depend on theta. So the probability of the data samples given t and theta is the same as the probability of the data samples given only t. In this case, if we know t, then theta is just unnecessary. Like, it does not really help us determine the probability of the samples. This definition is hard to check, so we have a theorem next, which makes it easier. But the idea is that statistician B only knows t, but since t is sufficient, they don't need to know theta in order to generate new samples from the distribution. So statistician B can actually just generate n ID samples from the distribution, just like statistician A. No one is at any disadvantage. Okay, so there is a criteria that helps us determine if a statistic is sufficient. So if x1 through xn are ID random samples with this likelihood, then a statistic is sufficient if and only if there exist non-negative functions g and h such that the likelihood of the data given theta can be decomposed as some function that depends on the entire data but not theta, and the function h, which can depend on theta, but only on the data through the sufficient statistic t. So in other words, theta and the data samples x1 through xn can't interact except through the sufficient statistic t. T is the only thing that allows the data and the parameter theta to interact. Okay, so let's do some examples. So if x1 through xn are ID random samples from a uniform distribution, let's show that the max is a sufficient statistic. So we write down the likelihood function as normal. So we showed in a previous video that it's 1 over theta to the n times the indicator of all the xi's being less than or equal to theta. So if all the xi's are less than or equal to theta, then the max is certainly less than or equal to theta. So the t statistic is also less than or equal to theta. And now if we choose g to be 1 and h to be this function, notice that h only depends on the sufficient statistic t and theta. It does not directly otherwise depend on the data samples x1 through xn. Okay, now let's consider if x1 through xn are ID from a Poisson distribution. And we want to show that the sum of the xi's is sufficient. And therefore, because the average is just the sum divided by n, the average would also be sufficient. So let's again write down the likelihood of the data given the parameters. Okay, so we can plug in the mass function and do some algebra to factorize it. We replace the sum of the xi's with t. And now, if we let g be the left term here, notice that g only depends on the xi's. It does not depend on theta. And also h here only depends on theta and the statistic t. It does not otherwise depend on the data samples x1 through xn. Okay, now what if they're from a Bernoulli distribution? Let's show that the sum is still a sufficient statistic. Okay, so write down the likelihood as normal, do some algebra, and then replace the sum of the xi's with t. And now if we just let g be 1 and h be this function here, h also only depends on the statistic t and theta. It does not have any other dependencies on the x1 through xn. It only looks at the statistic t that was computed from the data. Okay, now let's review the properties of estimators. So the bias of an estimator is just the difference between the expected value of the estimator minus the true value. And an estimator is unbiased if the bias is 0. The mean squared error of an estimator measures the expected squared error from the true value and can be decomposed into a bias term and a variance term, so there's a trade-off between the two. So if the variance decreases, then the bias has to increase and vice versa. Okay, so an estimator is consistent if it converges in probability to the true value. So for any epsilon, as you keep getting more and more data, the probability that the estimator differs from the true value by more than epsilon goes to 0. And now efficiency. An unbiased estimator is efficiency if it achieves the lowest variance possible. And then an estimator is sufficient if it satisfies the factorization criterion we talked about, so there exist non-negative functions g and h such that the likelihood can be decomposed into some function of the data samples only and some function of the estimator and the true value only. Thank you.